So welcome everybody. This is John Stewart. Glad you could join us for today's webinar. If my count is correct, this is the, actually it says right there, this is the 4th webinar in our series. What I would just like to say before we get to the introduction of the speaker is throughout the organization of the NGL project, we've consistently received feedback that as we move to the next generation of liquefaction models, it's very important that we take into account, to the extent that we can, geological conditions, not just geotechnical parameters. And we've really tried to take that very good advice to heart, and we're trying to figure out exactly how to implement that as we go into the model development phase. And so there's a number of ways we're doing it, but one of the ways we're doing it is we're going to hear from somebody who is an expert on that topic and has worked a great deal on it. And that's Monica Bucci. So with that, again, I thank you for joining us, and I will ask Kristen to introduce today's speaker, Monica.
Thank you. All right. So as John said, today we're welcoming Dr. Monica Jonah Bucci as our speaker. She received her bachelor's and master's degrees in Earth and Environmental Sciences at La Sapienza, University of Rome. She received her PhD in Earth Sciences from the Department of Soil Sciences at Lincoln University in New Zealand. And while she was there, she examined liquefaction features triggered by the 2010-2011 Canterbury earthquake sequence. Specifically, she investigated the links between surface manifestation of liquefaction and sedimentary aspects of the geomorphic features affected by liquefaction. Monica has been a research assistant at the University of Bari, where she investigated the sedimentological aspects of fossil liquefaction features of Mycenaean age and late Miocene, and distinguished liquefaction induced by seismic loading and by other triggers. And she also held a postdoc position at the University of Toronto to investigate paleoseismicity in Eastern Canada. And just beginning this past January, Monica became a Marie Curie Fellow at the University of Malta, and she is currently a visiting scientist at GeoMar in Kiel, Germany. Her project there is investigating spreading on subaqueous landslides offshore near Norway and New Zealand. So that's a wonderful bio, a wonderful person. I'm looking forward to hearing your presentation, Monica. I'll turn the time over to you. Let me make you the presenter.
Thank you very much, everybody, for having me and for asking me to join your webinar series. I'm very, very honored, and I feel very happy to have this chance. I'll start the sharing. Hopefully, I hope it goes well. Okay, can you see the screen, I think?
Yeah, looks good.
Yeah.
Okay. So in this brief talk, I will try to explain you what has been my the focus of my studies so far, and in particular, the research that I'm going to explain you and introduce to you is what I've been working on during my PhD. I had this wonderful opportunity of working at liquefaction triggered by the Canterbury earthquake sequence in Christchurch, and of using this experience to inform the local community, but also the scientific community on what can be valuable for investigating liquefaction features, and in particular the role of the sedimentological investigation and what we define then as the sedimentary architecture of the liquefaction features. So this talk is a huge also saying thanks to everybody who helped me during that time. So to the supervisory team at Lincoln University, at the GNS Science, and at Tish Stapleton, who allowed me to be here today, and to the fundings that we had, to the Natural Hazard Research Platform, who funded my PhD. So hopefully this talk can make justice to in a good way and can make a good summary of what was the essence of the work and what we found out also afterwards. Since this webinar series is about liquefaction and the surface manifestation of liquefaction and what are the different geotechnical and engineering geology approaches of the investigation and of study of these features, I'm pretty sure you are familiar with all these pictures. All these pictures are from different areas of Christchurch, Avondale, or QE2 parks, or also outside of Christchurch. The Halswell River was slightly outside southeastwards of Christchurch and was also badly affected by the liquefaction. And so all these images, I try to use these images in my presentation to show how this process, how this phenomenon was widespread into the region, into the city, into the region of the Canterbury Plains. So the outline of the talk will be to explain you why geologists pay attention to liquefaction features, and in particular, what type of features do we look for into the stratigraphic profile, why paleoliquefaction features are important, and then focus on the Canterbury earthquake sequence and the liquefaction that were triggered. When we investigate these liquefaction features, in particular, we find challenges in investigating the stratigraphic profile. So in order for geologists to investigate the stratigraphic profile, he has to be the soil, and so the surface deposits has to be dug, has to be further investigated with the excavation of trenches or holes that can allow us to see what the stratigraphy looks like. And liquefaction produce anomalies into the stratigraphy. So we see that in this case, there is a sort of regular semblow. So we see clearly and identify clearly the fresh, newly deposited sand on top of the ground. And then we see also very narrow feeder dikes. Of course, the size and the dimension of these features can vary. And this all depends by the magnitude of the earthquake, the peak ground acceleration, and of course, it depends strictly by the local geology. Here, this example that I've been showing is an example in the Taitapu area, so near the Halswell River, southwest of Christchurch. And it's a very small liquefaction dike, and but a consistent and quite large indeed semblow. But if we go in another area of the world, like for example the New Madoc seismic zone, we see that liquefaction features can have very different, can assume very different morphologies, and the type of soil stratigraphy that we find when we go out in the field and we investigate these features can be much more complicated. I had the fantastic opportunity of working with Tish Tuttle at dating and describing some of the liquefaction features that she spotted and that she investigated for a very long time in the New Madoc seismic zone. It is one of the areas where paleoliquefaction and then the related paleoseismicity investigation has been very much developed. So in this case, we see that the soil profile can be very altered by the liquefaction features, and we also see that sometimes these features don't appear at the surface. So we only can see these features when we investigate a fresh cut into the stratigraphy, or when we actually dig trenches. But otherwise, these features won't appear at the surface. So even more in these cases, it's even important to understand what are the landforms that are more susceptible to this phenomenon, and what is that stratigraphic and sedimentary architecture component that makes this feature to be more to occur with a higher likelihood. And this is another example of how the stratigraphy of the soil profile can be very, very complicated. When we look at this very complex stratigraphic profile with all the different units and the different morphologies that liquefaction dikes or sills or blows, in this case, ancient liquefaction features could be find, we also need to pay attention that these features, when we find evidence of charcoal or any organic material that is available to date, these structures are fundamental for understanding evidence of past liquefaction features. So for geologists who are working in the broad field of the paleoseismology and who are working for improving the seismic hazard of a specific site, these structures are of fundamental importance, because by dating old liquefaction features, and in particular by dating these structures over a wide region, it's important to understand not only that there was an earthquake, but it will be possible also to understand what was the potential magnitude of that earthquake, and if it wasn't possible to understand what type of fault was there, or what type of, if it wasn't possible to identify the fault or the seismogenic region, at least it was possible to identify where was located what often engineering or also paleoseismologists call the seismogenic center, energy center. So this is an important aspect of the liquefaction studies that is very important, especially for seismic hazard improvement and investigation. So why the Canterbury earthquake sequence was important? There was awareness. It's important to say that there was awareness of liquefaction features into the whole New Zealand. There were studies that were documented, they were documenting past evidence of liquefaction features in other areas of New Zealand. But none of these studies was taking into account the possibility of having extensive liquefaction features in Christchurch, and in particular of considering how badly these features could affect the city center of Christchurch, which was particularly affected in consequence of the 22nd of February 2011 Christchurch earthquake. So the Canterbury earthquake sequence has got 4 major events. In this map, you see 2 major events. But after the so the 4th of September Darfield earthquake, and then the 22nd of February 2011. But then there was also the June and December 2011 earthquakes, who were considered important aftershocks, and that also caused other liquefaction events. So it's very interesting to see what is the extent of these liquefaction features, in particular in consequence of these 2 events, and also how badly affected the areas of the coastal areas of Christchurch, and in particular north of Christchurch, Kaiapoi, were very much affected. We had a chance, while doing field work, we had a chance of investigating also, in particular, liquefaction features in the coastal area of Kaiapoi, which is this town, which is, of Christchurch, where you see the asking them what was their experience with these features, and we had people documenting with pictures and also reports from the AQC that they had their house impacted by the liquefaction events. more or less 5 times since the earthquake started, the earthquake sequence started. So for the local population, this was a very big stress and a very important impact, economical impact on the local urban community. When this happened, I had the opportunity of contributing with my PhD in trying to address these two big questions. Can we identify what are those geomorphic features that look like to be very much susceptible to liquefaction? And in particular, what is the role of the sedimentary architecture in all these? So we decided that it was important to start an investigation that would be more comprehensive, that would be more, that will take advantage of geological, but also geophysical and engineering geology techniques. So in terms of geology, we used the LiDAR that was surveyed before the earthquake sequence, but then after there was a very good data set of LiDAR, and this allowed us to have, along with topographic mapping and previous superficial geology mapping, a very good geomorphic analysis of the study sites that we decided to have. And then paleoseismic trenches cores, and so piston or vibro cores, and then dating of the material into the paleoseismic trenches, thin sections, which means understanding the microsedimentology. So we took very small samples of dikes and hosting sediment to understand at the microscope what is the fabric, what is the arrangement of the grains at the microscale, and understand where do we see differences between liquefaction and hosting sediments, and then of course grain size analysis. In terms of geophysics, the type of analysis that we used was the ground penetrating radar, with different frequencies, and we had the opportunity of running the ground penetrating radar at the alluvial site and at the coastal side using both 2D and 3D techniques, and we had different results. And then for the engineering geology aspect, the use of the cone penetration test was very much important. So while analyzing the whole Canterbury Plain and the liquefaction extent that you have seen into the previous slide, we ran a first analysis trying to understand what was the link with geomorphic features that were mapped. And we saw that alluvial site we are more susceptible to liquefaction features and coastal sites as well. So this has been also broadly acknowledged in the previous literature. So also our preliminary findings at that time were perfectly consistent with the literature that was available at that time. So we selected some study site in the rural area of Christchurch, in particular the Halswell River, as a specified before, and the coastal sites that were along the coastal area of Christchurch and a little bit north of Christchurch. So in this slide here, we saw how it was very useful, the LiDAR, the high resolution LiDAR that was that allowed us to have a digital elevation model of the area of the Halswell River, and it was very beautiful to see all these meandering shapes and all the landforms, the alluvial landforms that it was possible to highlight thanks to this high resolution LiDAR. And through the LiDAR also is possible to see what are the buried landforms. So all those landforms that aren't currently used by the river, that aren't currently active, like for example, paleomeander, that played an important role into this liquefaction analysis that we ran. And so it was very important at this first stage of the work to understand, to detail the type of mapping of the liquefaction ejecta that was possible to see using the aerial images that were taken just after the liquefaction events of the 2010. And so by detailing mapping these features, it was possible to see that there was a very, very strong correlation between the liquefaction features, especially at this site, the Halswell site, and also the Marchand sites, between the liquefaction ejecta and the Hinder meander belt of these active meander and paleomeanders. So at this site in particular, what is showing here is the Halswell site. We use this field site. That was an open field, was a farm area, so it was very good to see the natural topography of the area, and we had very nice farmers, very nice guests who helped us in welcomed us at the site, so that it wasn't difficult to interact with the local, and we were always very grateful for these. So we use this farm as a sort of natural laboratory where to investigate liquefaction features, and we used all the three techniques, all the three approaches that I've been mentioning a few minutes before with the use of geological techniques, geophysics, and CPT for the engineering geology side, to see what was the difference between the area that is characterized by many surface ejecta, high density of surface ejecta, and an area that doesn't look like to have surface ejecta. So we ran this transect, localizing trenches, cores, and CPT that were able to investigate the stratigraphy at depth, and trying to see what is the difference in the stratigraphy. So this is an example of what is possible to see in the course, and along the course we took grain-side samples, and it was possible to take grain-side samples, thin section samples, that are other samples, as I briefly explained before, that allows the researchers to see what is the microfabric, what is the grains arrangement at the different stage of the course, and it was, of course, possible once the course was split in half. It was possible to see if there was already evidence of subsediment deformations into the course, and in some cases, it was possible to see these. So, of course, were very much important to understand what is the stratigraphy of the deposit underneath the trenches, because for safety reason, we couldn't trench below 1.5 meters, since the water table at that was already 1.3 or something. So when trenching, there is, of course, the problem of the water table coming up. And so the course can help in understanding the stratigraphy, and then also the CPT will help in understanding what is at least the sediment at depth, more in depth. And so this was a summary of the use of all the three techniques, all the three aspects of the work. So geological techniques, geophysical techniques, and engineering geology, CPTs. So this is a profile that shows the transect that I've been showing you before from Hardwicks 1, that is right on the, Hardwicks 6, and one that is right on the paleomeander covered by crevasse clay deposit, and then far into the floodplain where we couldn't see evidence of liquefaction features. So this is a correlation, or cross section, as it's possible to call, and it contains all the geological information that we will get out of our synthesis. And it was also possible, and so by using in synergy with all these techniques that were used, we could delineate the sedimentary architecture at this site, and in particular along this profile. So we could see that where liquefaction were very highly concentrated, there was a paleomeander that contained clean sand, and then on top of these there was a sort of clay plug or finer sediment that created a sort of higher elevation area. So where there was clean sand, there was often the source of the sediment, but the major difference between where we could find liquefaction features exposed at the surface, so sand blows at the surface or cracks at the surface in the case of lateral spreading, and study areas where there was, again, clean sand or liquefiable sediment, but no surface evidence at the surface, was an important stratigraphic difference. So in the cases where in that area where liquefaction features was not observed at the surface, there was an alternation of sandy sediments with clay lenses that potentially didn't contain the liquefied sediment, while in other cases, when we saw a very thick liquefiable layer, a very thick clean sand layer in correspondence of paleomeander bars and point bars were features, fluvial features, very much susceptible to this phenomenon, we found that the stratigraphic discontinuities that characterize the alluvial point bars were so much susceptible to liquefaction because the stratigraphic discontinuity could allow the venting of the sediments at the surface. And this was very interesting to discover. And what was very interesting was that our study, our conclusions, our findings were also consistent with other geotechnical studies that were carried out by other research groups in Christchurch, and in particular by the Canterbury University and its team of researchers. And in particular, in a study that Misko Kublinowski led, he found out, after doing so many CPTs in the Christchurch areas, he found out that all the CPTs could be, all the sites from the CPT's analysis could be investigated, could be classified, into two major sites, the double Y sites and the double N, double negative sites. So at the sites where where the team investigated has double negative sites, he found, as well as in our cases, he found that there was an interlayering of sand, so thick sand layers, but with the presence of clay layers. And these were often floodplain sites, that because geologically speaking, floodplains are characterized by abundance of silty sandy silty sediments, and clay lenses. While where we had paleomeander or meander rivers or point bar deposits, so the features that I've been showing you in the before into the cross sections where we have thicker sandy clean sand, there was evidence of liquefaction features at the surface, and so those were the double Y sites that were showing at each liquefaction event surface deposit of liquefaction. So this was a very important consistency between the two sites that were carried independently, and we also found out about these afterwards. So as it was stated in the study by Kublinowski et al., the system response is very important when investigating liquefaction features. So the stratigraphic complex and the stratigraphic architecture of each site where the CPT is driven is very much important to understand how the stratigraphy behaves and how can be possible to see evidence of liquefaction features at one side and not in another side. So this slide is a little bit of a synthesis of our geological investigation and our holistic investigation using not only geological tools, but also geophysics and CPTs and the system response analysis that was carried by Kublinowski. And so here we see a simplified model of fluvial geomorphology, where we have been focusing in this case, and different grain size that is possible to see. And so we can see that has been showing into the model before, Palmer deposits, due to their discontinuity and stratigraphic discontinuity, and also specific gentle inclinations, allow, and also being very rich of clean sand, allow the sediment to come up at the surface more easily than floodplains deposits that are characterized by a constant bedding that potentially make the liquefaction occurring, but these features, these sediment do not travel at the surface due to the interlayering and interbedding of the sediment and the alternation of silt and clay, sand and clay lenses. So this is my contribution for your webinar, and these are some of the references, key references that I've been using and mentioning into this work. And so I'm very, very grateful for this opportunity and for allowing me to join your webinars. And so my current work now is in understanding better what is the role of the liquefaction and also of the clay softening into the for spreading mechanism, and in particular for spreading into the subaqueous setting. So my research is going into this direction now, and hopefully I'll be able to contribute in a good way. We'll see. Yeah, I've just started this project, so I'm also very happy and very I'm very happy to join your NGL group, because I'll be very curious to discuss the spreading dynamics and other mechanism for related to the spreading morphology offshore in the subaqueous environment. So that's for me. If you have any questions, please feel free to email me or to ask me. Hopefully I've been enough clear during this presentation. Thank you very much for this chance, for this opportunity.
Thank you, Monica. Very interesting presentation. I'll just remind all the attendees that you're welcome to raise your hand with the raise hand feature, and I can unmute you one at a time to ask questions, or you can write it in the chat or the Q&A. But let's see. John, did you have something else to say first? Okay, great.
I have a question. Monica, thank you. Great presentation. So at the beginning, so one of the things I was curious about is when you have 2 or 3 events in the same field, what does the prior deformation do to subsequent susceptibility of the soils to continue to liquefy?
Yeah, this happened. This has happened, and while we were excavating trenches, in particular at the coastal sites, the features that I've been showing and the study case that I've showed you so far in this webinar is mainly for alluvial sites. But in the coastal sites, it was very tricky to see and to discriminate the different events. So often you see that the same dikes get reactivated, and when there is not much distance, in time between the different liquefaction events, you don't really can clearly discriminate. But if there is when this happens, micromorphology analysis, so as I showed you, the thin section analysis, we wrote a paper on this and how it's important to evaluate the fabric of the sediment. This type of analysis can potentially help in discriminating and in understanding that perhaps within the same liquefaction, within the same earthquake sequence, there were multiple and close in time liquefaction events that perhaps reactivated the same structures. In case there is much more time that goes by, and you see, now, for example, after 2 centuries or more time, you can actually date the deposits, and even though there could have been the same structures, you can find evidence of different stratigraphy. And yeah, the analysis, it can be very complicated. The analysis of a complete wall and a complete stratigraphy, and also at different sites, that can help in understanding how many vents did we have, how many vents is it possible to see. Yeah.
Wow.
It's not always easy. Yeah.
But it's surprising that it's so regular. Like, I would think that one liquefaction event would so mess up the soil that the next one would not. Yeah.
Yeah.
I have more, but Kristen, but I'll let others ask questions. I'll come back.
Okay, sounds good. I saw Scott Brandenburg has his hand up, so I'll send him an invite to unmute if you'd like to ask a question.
Okay, thanks. I think I'm unmuted. Can you hear me okay?
Yeah.
Great. All right. Thanks, Monica, for delivering a very nice presentation. I enjoyed it a lot. My question is about kind of the last slide you showed right before your citations with the point bar deposits and then kind of the floodplain deposits off to the right side with the fine-grained soil interbedded. And it's about the effect of groundwater table depth on the system behavior that you observed and Mieszko has talked about as well. Did you find that manifestations were more likely at locations where the groundwater was very shallow or a little bit deeper because, you know, the presence of a soil crust above groundwater acts kind of like a pump to create an upward hydraulic gradient that's bigger than if the groundwater is right at the surface?
Yes, and this turned out to be a very interesting aspect, especially in the coastal side, because there is a higher susceptibility at the coastal side because the water table is so shallow and the sediment was so sorted also that was easily entrained and manifesting liquefaction. So yes, definitely, where groundwater table when groundwater table is shallower, we can find evidence of there is a higher likelihood of the soil to liquefy. And yeah, definitely this plays, and also the season sometimes. I remember when we were analyzing the aerial photos and doing the geomorphic investigation, it's very important to understand also which season was in which season these events occurred, because the water table was different. So that's definitely an aspect that is important to keep in mind when investigating these sites that are very susceptible, and what is the position and how shallow is the water table at the surface. Yeah, that's important.
Right, great, thank you.
I'm looking for a raised hand. I see John Stewart has one, so go for it, John.
Okay, thanks, Kristen. I really enjoyed the presentation, Monica, great job.
Thanks.
So my question is going to be a very sort of from a geotechnical engineering perspective, because that's what I am, and very practical perspective, which is I definitely take your point about the importance of the system effects. I think that's been observed quite definitively in Christchurch, and you know, I think we all believe that. One of the challenges we have as geotechnical engineers trying to model liquefaction is that sometimes we don't have enough information to necessarily tell that these system effects will be there. You know, I think of a case, for example, where we have a boring, we might have a few SPT blow counts in different units within that boring. And we might suspect it, but we may not really have enough detail on the stratigraphy to know. And so what I'm trying to think of is whether the geological conditions that can be mapped near the surface could help us identify locations where these system effects, these interlayering features you were speaking of, are more likely and where they're less likely, such that even if we don't know the details of the stratigraphy to say that for sure a system effect is there, we might be able to make an educated guess based on the geology that it's there. And you know, you talked about floodplains and point bars. given your experience here, and I know you've worked in many places around the world, do you think that there's kind of a consensus on these are the types of units where you're likely to see the system effects, and here's another set of units where you're less likely to see it that we could perhaps use in this project?
Yes, like definitely. Also in the literature, like looking at the literature and when reviewing the literature that talks about superficial deposits that are more likely to show evidence of liquefaction, or just show a higher susceptibility of liquefaction. Yes, this information is already available, like the meanders and point bars tend to be always more susceptible in showing evidence of liquefaction features at the surface. But the problem here is that even if we don't see liquefaction features at the surface, we still have liquefiable material at depth. So the floodplain, yes, perhaps at some point of the floodplain, you do not see liquefaction features at the surface, or maybe there might be some structures that behave like conduit that can allow the sediment to travel upwards. But so I guess the problem is trying to see that even though there might be a site that is not considered to show surface evidence of liquefaction features, you still need to understand what the material is there and what is the sedimentary architecture, because perhaps that can lead to underestimate the liquefiable susceptibility at that site. And so for an infrastructure or for the basement of, for the foundation of infrastructure or of buildings, dwellings, anything, that can be an issue. So yes, like the classification of geomorphic features is something that has been investigated in the past, and with this study we showed what are the differences and how the deposits are structured and are organized. But what I guess is important is to see, okay, here the liquefaction don't come out to the surface, but still can be an issue at depth. So that's I think is the problem. So yeah, so doing an educated guess on this is yeah, this is something that perhaps there still needs to be like more understanding in this direction, because also it depends where the potential liquefiable layer is, and then perhaps the depth maybe is a considerable depth, and perhaps can be not considered as a very huge issue for the dwelling, or the other way around. So my understanding so far is that the strictly geological conditions, like the really local conditions, since there is a high variability in these, need to be investigated properly in each setting, because it's not possible to, perhaps at this stage of techniques, to say, okay, I classify all these sites in this way, and we have this type of layering at these sites. Yeah, like yes, there are some features that are more susceptible, but the local conditions the local geological condition can vary in a high way. So that will need to be investigated properly.
Yeah, great, thank you.
Yeah.
So I received a question from Tish, and from Tish Tuttle, and I also see Kevin Frankie's hand up. So I'll give Tish a chance to answer, or to ask her question in person first, and then I'll give Kevin a chance.
Okay.
Hi there, Monica.
All right.
Hi, Tish.
Hi, nice to see you.
Yeah, thank you.
And thank you very much. So I'm interested in this idea of sites that liquefy at depth, but show no evidence of liquefaction at the surface. And that's important for both geotechnical studies, for foundation failures, but also for paleoliquefaction studies. But you showed some soft sediment deformation features in cores from one of the sites.
Yeah.
And how convinced are you that those are related to earthquake-induced liquefaction? And the other question is, did you find that the GPR showed disturbance? You know, was the GPR able to detect the disturbance in those same layers? Are the features large enough for GPR to detect them?
So at this site, I'll answer to the GPR question first. Thanks, Tisha, this question. So at this site, I remember we had several issues in investigating and in finding what the GPR was detecting with the liquefaction features that were spotted at the surface and in the trench, sorry. But because sometimes the size of the liquefaction features is very important, and I remember in one of your study cases, the GPR was very effective also because the liquefaction features that you have in your areas are much bigger, and so the dikes are wider. I remember when there was the GPR campaign at the Halswell and Marsham sites, unfortunately, that GPR campaign was done afterwards, the trench campaign, and only a specific trench, like Marsham 4, or was possible to see the blisters. And so probably because the sand deposit in the blister was wider, and so it was nicely correlated, and this is in pillar and it was nicely correlated. But otherwise, at the other alluvial sites, because the dikes were so narrow, it wasn't always very easy to detect. Maybe you see anomalies and you see like what the GPR profile looks like is very like in the subsurface, it looks very disturbed radiogram, and we see anomalies, and then we thought that those features could have been liquefaction features. So yes, at the alluvial sites there were some issues. For the coastal sites, that were the sites that I directly ran the GPR on, I can say that the GPR there was very, very useful because it really helped, since the campaign at the coastal sites was done after 4 years from the liquefaction events. In the parks and the areas that we investigated were all completely covered and completely all recovered by the liquefaction event. At those sites, the GPR really helped in investigating and in digging trenches where exactly was that liquefaction deposit. So at that case, although sometimes the correlation between the radiogram and the trench stratigraphy, it's not always straightforward, but it's effective. The system, the GPR is very effective. And so for summarizing the answer to your question, yes, the size of the features that you want to target is very important. And if they are too narrow, sometimes you probably don't see them clearly. And in terms of coring, I remember the reason why we investigate, or the reason why we understood that that sand was the same liquefiable, the same sand. The reason how we found that the sand into the core was the sand that was exposed into the trench stratigraphy, was grain size analysis. So through the grain size analysis, we will see the same spectrum of the grain size distribution, and it was possible then to see that the subsediment deformation that were briefly seen into the core could have been seen also, was the same grain size at the surface in the trench, I mean. But of course, for paleoliquefaction analysis and for much deeper paleoseismic investigation, cores are not enough. Like cores can help because they give us a sort of picture of what is the stratigraphy under the trenches. But no, like I would suggest to have trenches and paleoseismic trenches rather than only cores. Yeah.
Okay, thank you.
Yeah, I don't know, maybe you have a much better answer for these.
No, that was very good. Yeah, thank you.
Let's see, Kevin, did you still have a question for us?
Yeah, thanks, Kristen. And hi, Monica. Great job on your presentation
Hi.
today.
Hi, thank you.
Yeah, my question is similar to Tish's question, and it's just a follow-up. As geotechnical engineers with our simplified triggering models, they are all based on evidences of surface manifestation, but the sticky part of that issue is the possibility of liquefaction occurring that does not cause a surface manifestation. And so I'm just curious, if in the trenches that you performed in these areas that showed no surface manifestations of liquefaction, what was the frequency that you observed evidences of subsurface liquefaction? Was it a common feature that you saw, or was it rare for you to find evidences of subsurface liquefaction in these thin interbedded layers?
So the only reason why we know that the sediment was liquefiable, like at those trenches that didn't show surface evidence of liquefaction features, there wasn't really dikes or that I remember also. I'm not sure Tish maybe also remembers, but how we knew that it was liquefiable material, it was through the CPT. So at that site where we had a trench that and there was not some below at the surface, we did not see dikes or other liquefaction features. Yeah. So
okay, but just to be clear, so I understand, when you performed a trench in those soils, you also did not commonly see dikes in the layers beneath the ground in those thinly interbeds. Is that correct?
May I interject, Monica?
yes, of course, yes.
Yeah, so there, in at least one of the trenches at the Hallwells site, there were small dikes that did not make it to the surface. And you could actually, it looked like you could see the source depth in as well. Of course, as Monica mentioned, that the water table was fairly high, so we were somewhat limited and it was fairly gooey. But you also, at other locations, like where Monica and I looked at liquefaction features exposed in river cut banks. Now, this would be in the central US, that we saw plenty of evidence of liquefaction features in cut banks, sand dikes that did not make it to the surface. So in some cases, we would see the source beds as well. So there are places out there where you get liquefaction at depth and no evidence of liquefaction at the surface. So that's why I was curious to know about these other techniques for exploring those sorts of sites.
Mm-hmm. Yeah, very interesting. Thank you.
Thank you for asking your questions. Do we have another? At the moment, I don't see one.
Well, I may ask a quick question before closing the webinar. And Monica, like everyone else, I enjoyed this very much. You provided a lot of very, very useful information for us. In geotechnical engineering, and you know, we've seen and always, I'm always noted to the complexity of the both the depositional environment and the hydraulic environment that we see in some of the photographs that you've shown and that others have shown, like Tish, over the years. The formation of these sand boils or surface evidence is a very, very complicated three-dimensional process. And we in geotechnical engineering usually have information that is one-dimensional. We have either a boring or a cone penetration log, and we're trying to develop our triggering procedures on the basis of that kind of information, where we don't have a picture of the lateral variability of the soils. And I'm wondering if, in your experience, that if there is say a minimum thickness of a fine-grained layer that you think would allow it to serve as a barrier to the upward flow of water. If we see a 1 centimeter thick layer of clay in a cone penetration sounding, is that something we should consider to be an aquiclude, or would its lateral extent be so small, or its strength be so small that it would not serve as a barrier to the flow of water? Do you have any sense of that?
No, we didn't get to this threshold. Like, we didn't do any type of calculation for understanding what is the thickness of the clay layers that has to be in place in order for the liquefiable material to not come out to the surface. No, I don't have any number, any size or thickness that I could be confident in saying. No, that's not something that that I still had a chance of working on. No, I'm sorry, Steve. That's not something that I can say. Like, I don't feel confident in saying, oh, this thickness is enough to being for sure. The interbedding, for my understanding, the interbedding of sand and clay can like represent an ideal situation for having the liquefaction of the layer, but still not the fluidification, so not the sediment will travel at the surface. But I cannot say confidently that I haven't like a threshold of the thickness of the clay layers. No, I'm sorry, I don't have these. We still didn't go into that direction of study, but perhaps this can be a type of work that can be more that can be done. Yes.
Yes, there are probably plenty of cases that could be looked at to gather that sort of information.
Mm-hmm.
That would be perhaps a useful direction to go in.
Thank you, Monica and Tish. I asked the question thinking there's probably no real answer to it at this point, but it is something that we have to take into account in trying to develop models that predict triggering or predict surface manifestation. We are at 11 o'clock, at least our time, and I'd like to close the webinar by thanking you again. You've identified many important and fundamental issues in not just in the evaluation of triggering of liquefaction, but that also have impacts on the consequences of liquefaction. So you've given us a lot of food for thought and for future discussion, and we really appreciate it. And I suspect that at some point in the future, at least our modeling team may have a few more questions for you, and hope that we can remain in touch through that process. So thank you, everybody, for attending the webinar, and we hope to see you at future webinars that will be announced as they're organized. So, thanks very much.
Thanks, Monica.
Thank you. Thanks, Monica.
Thank you, Tish. Bye.
Bye-bye.